So
Yes, and you see now there is a light here.
I think the light turns off soon. I think like
Okay, now it's on.
you see another light still on. Let's see the ring. What's
You
in it?
already tried to find out what exactly the
there's-
sin is. I don't know. I never checked. It's
You
a
can't,
mystery.
you can't actually see the back of it, except it's a 3-terminal.
Yeah, you can try to
Yeah.
identify this.
The problem is that maybe the switch is.
Well, it's industrial age. I've got now. Piss off.
You're going to be sharing the slides, right?
Yes, I'll do slides.
I
You can
will-
do all the talking. I'll do slides.
I'll just let people
What
know.
else is this cheap shit?
Well, not being a plastic has a problem. If there is a.
Oh, you're holding buckets back inside.
Well done. Oh, sometimes cheap plastic is better. I think it's amazing.
But it's heavily over-engineered.
Yes.
What would be the application of even and you've got them everywhere, I take it.
Do you think we should start?
Yeah, I guess
Have a
we should
minute?
start with slowly.
I mean, administrivia is going to take us 2 minutes, so we can give it another minute or two.
Okay, so, but
Just because it's the first session on the first day, it's always.
yeah, people are lost.
Or they haven't seen each other and they want to chat.
We're gonna see each other for the whole week. So that's,
Sure.
so that's cute.
But they're like, hi, how are you? It's been ages since I've seen you.
Like 1 minute.
I wonder if the mic's on. Probably. People are listening to microphone.
Yeah, it says 15 amps, but probably it's the total. Yeah, because the size of the board.
Go for it. Slow start.
Hello, everybody. Jen said I should do a slow start, and so we're slowly starting. I also figured if I spoke slowly and in a calm voice, people would stop talking and would start. Ooh, it worked. Hello, everybody. Welcome to IEPG. We have a new co-chair this time. Thanks, everyone. Say hi to Jen. Whee! Jen!
More Comic Sans.
Chris hasn't been able to come to the meetings for the past while, and so it made sense for somebody who's actually here to do it. And Jen's been helping for the past while. So, hello, welcome, Jen. As you can probably guess from the font on the slides, either Jen Linkova or Randy Bush made them. And the background is sort of orangey pinkish color, and so it must be a Jen presentation, or the projector is very badly set up, white balance and things. So this is IEPG. It is an informal gathering that meets on the Sunday prior to IETF meetings. More details are in that RFC, which is actually written by Jeff, so this is all his fault. The intended theme is operational stuff like measurement or, even better operational issues people discovered, things you should know when operating a network, etc. For a while, it used to all be basically, DNS all the time or BGP all the time. It's now branched out a little bit. Yeah, it's never been V6 all the time. There's no V6 already. We said operational stuff, deployed things, not theoretical future coming. Oh. So we have an agenda. Thank you, everybody who has submitted slides and stuff. This is our agenda. Apparently, somebody doesn't know how to spell local root. It's actually loco root, and so
From your spreadsheet, actually.
bugger. So this is our agenda. I would say agenda bashing, but don't bother doing that because we're not changing anything now. So, with no further ado, it is making local root the default.
Yeah, just voice control.
Do
Voice
you
control.
want to use? Okay, yeah, voice control.
I'm Jeff Houston. These were Warren slides originally, but I hacked and slashed and bashed at them. So very little actually. Oh God, my voice is normally big enough and loud enough, but okay, if that's
You're
what you want.
Too tall.
I'm sure they can. There we go. So yes, these were originally Warren slides, but they've been heavily hacked, slashed and battered. So I will take responsibility for them. Next slide. This is actually about the DNS and trying to change one of the more, you could say one of the more fundamental behaviors. Logically, not actually, logically, every DNS resolution starts at the root. The whole reason why the DNS works, though, is that most resolvers cache wherever they can, however they can, and therefore they don't ask the root once they already know that .com exists and here it's servers, .net exists, blah, blah, blah. If you have an amnesiac resolver, i.e. one that doesn't work, or you're just booting up though, the root has to actually be there and answer, or you have no idea what you're doing. So the root is kind of at the start of all forms of DNS resolution, because that's the only way you can find where the authoritative name servers are for a zone. Next slide. The good folk who run the, 12 or 13, you can argue whether VeriSign with A and J are 2 or 1, but the good folk who do run the existing root servers do a huge amount of data. And if you go to, well, anywhere really that has the RSAC 002 data, you can pull down a whole bunch of stats over time about what the roots are doing. And the one I've done here is a collation of all the stats over queries. And I've forgotten whether it's queries per second, every hour or minute or whatever, but you can see that these are totals, that the query load aggregate that all the root servers actually serve is variable. And next slide. Chrome, when it started up, used to want to know what was the DNS environment that it was sitting in. And in particular, it was trying to find out if folk were synthesizing effectively non-existent domains. So it used to bash away when it started and produce a couple of queries for single label long names. I think there were 17 characters, alphanumerics, random, and they started calling them chromoids. A lot of people run Chrome. 68% of the world's users evidently run Chrome. And when every time you start up Chrome, you bash away at the root, because normally caching non-existent random names is kind of useless because they're random. So they're never going to ask for the same one again. It all hits the root. And when Google got a clue, I can't see that vertical bar, somewhere in 2021 and just stopped. Interestingly, the query load stopped. Who said the internet was slow on trying to do software upgrades? Because in Chrome's case, that was actually pretty effective from day one when they released it. Just bang, it stopped. Next slide. But then you'd think, oh, this would slow down a bit. But in the last 2 years, it's risen from around 90 billion queries a day in total up to 130 billion. Next slide. Which is a fair amount of growth. Around 40, a little over 40% over 2 years. Now, if you look at the last 2 years and look at your business, almost nothing has grown by that rate. Most of the markets we look at, mobile or fixed, are actually looking in severe saturation. We're topping off on a whole bunch of things and stats about the net, because quite frankly, how many pockets do you have for mobile phones? How many more places can you jam a SIM in? I'm like, at some point, human ingenuity just fails us and we just can't stuff this stuff anywhere else. And we're finding those limits. And if you look at the growth rates in this industry, it's gone from greenfields to replacement. And even there, as the speed of new processors, slows down, and the only difference between this year's Mac and last year's Mac is the color black or gray or whatever it is, that's the only difference, then you tend to realize this market's actually saturating. And so here is something that's not. And 40% growth over 2 years is definitely not saturation. And the other thing is too, queries to the root servers come from resolvers if everyone's well behaved. And the only time the resolver queries a root server is when it hasn't got it in its cache. So it should be looking at a miss rate from recursive resolvers. 130 billion queries a day doesn't seem to tally. So whatever's going on at the root, that's weird. Next slide. But what's even weirder is the economics of the DNS, and in particular, the economics of the root. Because normally, the internet isn't free. You know, shock horror, despite all the hippies from the early 90s. It's not. You pay for it. Everyone pays for it. Somebody always pays for it. And the amount you pay in classic economic theory is basically the cost of what it takes to produce it, plus margins. So in general, under that kind of model, the more you consume, the more the incentive to produce more because they're getting money. So, you know, I buy widgets, I buy 10 times more widgets. The widget manufacturer goes, yeah, I need to make 10 times more widgets, off we go. But the DNS is not explicitly funded. There are a few DNS service providers who actually charge to host the domain by query volume, but that's few and far between. Most of the time, it's all bundled. So although the DNS is unfunded, if you're paying your internet service provider some monthly fee, then part of that is you're covering the cost of operating a recursive resolver inside that ISP, and it's just all bundled up. And what about authoritative name servers? Well, if you've got a domain name and you want it hosted somewhere, you pay. Or you can host it on your own machine, but you're paying for that machine's electricity, connectivity, blah, blah, blah. So in general, even though there's no overt cost per query, the stuff is paid for. Otherwise, it wouldn't exist, except for the root zone. And bizarrely, no one pays for that. Nobody. It's kind of a free service. Next slide. So you've got this inherent contradiction of a service that's growing, and 40% over 2 years is not a small growth. It just continues to grow. And there's no matching visible revenue stream. So obviously the root zone needs to track growth. Otherwise, root zones wouldn't get answered, root zone queries wouldn't get answered, and general badness would ensue. So somehow there is a need to escalate the investment in this infrastructure, but no visible source of funding to actually fund it. You're relying on the altruism of 12 unique operators spread around the world to actually do this stuff for you, which is kind of weird in this day and age. Next slide. So the basic problem actually still isn't money yet. It's kind of, how do you scale the root service? How do you grow by this 40% over 2 years? Next slide. Anyone remember the Yeti project? Shane's online. He was the one who actually did some work, was working for them, not many others. I think Joao remembers it. It was a project with Chinese sponsorship, and I seem to remember Paul Vixie's hands all over it, to try and prove that 13 was just a number. And Yeti tried to expand the number of root servers in this pseudo root zone well beyond it. The problem is the priming response and the behavior of the DNS. Back in the deep, dark dawn of time before most of you were born, all of you actually, Paul Mockapetris had defined the DNS and said answers in UDP must be no more than 512 octets. You can go higher, but there's no guarantee anyone's going to receive it. If you sit at 512, there is some level of assurance that one way or another, even including fragmentation, 512 will make it, was the idea behind the DNS. So oddly enough, that 512 was what actually gives us 13 root name servers at the time in a v4 only world. Because it is possible to produce who serves the root, the answer of the names and v4 addresses in under 512 octets. Now, of course, we added v6. Oops. And the current answer is not 512, it's 811. So we've blown that number. But the theory is kind of, you don't really want to blow it by a lot. Because once you get into beyond 1500, you get into fragmentation loss, that doesn't work. Once you try and get well beyond that, you're going into TCP land. switching over from UDP to TCP is a nightmare. This is the priming query. Abandon all hope. Go and do something other than the DNS because that won't work. So in some ways, adding more letters doesn't really give the DNS more resilience in terms of a service. It's not a productive approach. Next slide. So why don't we just increase this inherent parallelism, because we have embraced Anycast like crazy. And some of these letters, and this is an old one. This is March 2025. Didn't I see a posting somewhere that it hit 2,000 now?
2 or 3 days ago.
Yay. So much Anycast. But think about this for a second. What are you relying on to make Anycast work? And you're relying on BGP. And Anycast tries to differentiate across BGP advertisements. Now, if we were a long, stringy network where each AS path had, say, 20 entries in it, then Anycast would be hideously effective. Because in essence, there's a huge amount of path variation where Anycast can actually drive in and say, there's a better path. The average AS path length of the internet, 4 going to 3. We are a short, fat, dense network. And in short, fat, dense networks, Anycast kind of doesn't work, It doesn't differentiate because none of the paths are long enough to actually do that. So in some ways, you don't get effective load balancing and distribution, even when you get to 2,000. There'll still be dramatic hot points and points where just nothing happens. So it doesn't mean we're shedding the load across 2,000 points. It's a lot less efficient than that. And Anycast is kind of, you build this enormous thing just to scale its capacity by a little bit. It's not very good economics. Next slide. So I said that. We're facing a 20% compound growth rate, but it's exponential. But none of these approaches seem to give us the tools and techniques we need. And by the way, we're not even paying for it anyway. Whoops. Next. So we've tried other approaches, and interestingly, they haven't really engaged. One of the better ones was actually using the fact that the route is signed. I was just checking the time, see how I'm going. Most of the answers that the root zone sees is negative responses. No, that's a crap name. This is the percentage of all queries that are answered with a no since 2015 or so. And at the time of chromoids, you see it reach a high of up around 80, 90%. And the reason why the negatives hit the root is that the treatment of negatives further down is kind of different. And if all the negatives are randomly generated, they weren't there before. So negative queries that are randomly generated will always hit the root. Aggressive NSEC caching was meant to stop that. Because when I say this name doesn't exist, what I actually say in DNSSEC terms is all the names between A, this exists, and some other label, B, that exists, all the names in between don't exist. Use the span to subsequently answer all the labels between A and B. In theory, if all the recursive resolvers were doing aggressive NSEC caching, that should disappear. We've had this out for years as a, I think it's a RFC standard.
Standard, I think.
Standard. Hasn't really done a huge dent. We're still up around 50% of all queries. So aggressive NSEC caching hasn't really gained traction. Next slide. Oh, there was another one there that simply illustrated the fact that, it came down but didn't get better. By the way, it's on by default in some of them. Bind supports it, Unbound not. All the recursive resolvers certainly have this code, but the negative domain rate at the root, as you saw, is kind of not going away. So how can we make local caching better? Next slide. It's a tiny domain zone, 2.2 megs. It's nothing. Have the entire zone locally and work from it. Never ask the root again. We actually have introduced, a year ago, the zone MD record into the root zone. This is a record that says, here are the contents of the zone. By the way, this is its signature. You can actually ensure that the zone you have received is the authentic zone because it's signed with the same KSK. So in essence, because it's signed, you can get a copy of the root zone from anywhere, check that the signature is valid and current, and then you have your own root zone in your recursive resolver. You're not sharing all of your priceless secrets with a whole bunch of root zone operators or anyone else. It's private, because now the recursive resolver looks up its local copy of the root zone and figures out what to do next without asking for anyone. It's fast, it kind of works. RFC 8806, and it advocated using AXFR, but quite frankly, it's signed. You could pick it up from the rubbish bin out there if you wanted. If the signatures work, it's valid and complete. Next slide. On the IANA page, here's a URL. You can go there and get the root zone if you want. Next slide. How? There's a one-liner in bind. Zone.type mirror. God, that's clever. Not says a little bit more, and it actually works away from the AXFR. Here's the root, and here's a URL. Go over there. You can use the one that's been provided for you, the one at Internet, or you can go and find someone else that's serving the root zone already from a URL. Zone doesn't care as long as it validates with the zone MD record. Unbound, again, a URL. But it's exactly the same idea. So the three most popular recursive resolvers out there have certainly done the work. Next slide. And the issue is, why isn't this the default? Why aren't you all doing it? It makes things faster. It really does. It certainly improves privacy because you're not broadcasting your queries to not only all and sundry, but a whole bunch of folk you don't intend to broadcast it to. The attack surface for attacking the root has disappeared because if you're mounting a DNS attack and your queries are going through DNS resolvers, the resolvers will absorb all that noise straight away. They won't get reflected back up into the root. And if you're really worried about how much of the world you're relying on to make your service work, and I know that there are folk looking at Amazon saying, were we really that dependent on Amazon AWS? And the answer is yes, you were. If you want to reduce those kind of dependencies, then the more you can lift into your own infrastructure and resolve and service directly, kind of the more assured you can feel about your own survivability. That should be the last slide. Is it? Oh, God. Oh, that's right. It's a great idea. Let's make it the default. Let's fall back to incremental queries only when you can't fetch the entire zone. And this draft, Warren's got his name all over it, is being discussed this week. And the whole idea is, let's make it the default. There shouldn't be another slide. Is there another slide? Oh, there isn't. There's enough room for questions though, so thanks.
Oh, Joe.
Hi, Jeff. Oh, is this working? Can you hear
Evidently,
me?
you've got to do this.
Got to get right close
Very,
to it.
very intimate, Joe.
All right, all right. Joe Abley, Cloudflare. I think it's interesting that aggressive negative caching doesn't seem to make a big impact in the percentage of negative responses. And it makes me wonder a little bit about percentage of what. So we know from running recursive service that we see an awful lot of junk. Some of it's from the kinds of clients that, for example, if we return TC equals 1, they will respond correctly and do a TC. So it's a real resolver looking thing. We also receive an awful lot of queries from things that are not real resolver looking things, a lot of embedded devices and compromised webcams and things like that. I wonder whether if that graph was measuring something a bit different, we might see that real resolvers, which have aggressive negative caching on by default in bind, not recursive, powered recursive and unbound and things, maybe they already are avoiding sending these queries. And maybe
Joe,
what we're seeing is a massive increase in other junk.
It's a great question.
Yeah.
And it'd be really interesting to compare the data from a recursive resolver, Cloudflare's, with the data from a root name server who'd cooperate. We're looking for one, and try and figure out why Cloudflare's NX domain rate is between 2 and 2.1%, because I know,
Yeah, yeah.
and why the root servers are reporting with RSAC 002 50 to 60%. It's kind of what is going on that the root is kind of laboring so badly when in theory the recursives are doing aggressive insect caching. Oddly enough, we need more data. And the problem is in the DNS, data is really difficult to get hold of. I mean,
Yeah.
it's just the way it is.
I mean, the what you're describing here as the solution, it has some concerns, but the concerns are mainly addressed by the people who've implemented it, who know what they're doing. So it seems fine, to be honest. But I wonder whether even once we do this, even after that's been seen wide uptake, we might still see a large proportion of junk at the roots, and we're not entirely sure which problem we've solved. So I don't know. Like, you already have our data, so I can't offer you that. But
Shunting load
Yeah.
down onto the recursive seems like a fine place to shunt load. Shunting it up into areas you're not paying for seems like a regressive fallback to the 1970s. Oh, you hippie.
Petr Špaček, ISC. There are a couple of things in your slides. You said that the bind has aggressive insect caching enabled since the 9.12, but in fact it was enabled in 9.18 because in 9.12 it was implemented, but it was so broken that we had to disable it again. So it's enabled in 9.18, which was released in beginning of 2022. And there is awful lot of Red Hat and all other crap distributions which ship 9.16 and older still. So people just didn't upgrade. But I agree with the previous speaker that, you know, most of the traffic at root is, in my opinion, not a real resolver. So even though hyper local root, whatever we call it, might help to actual resolvers, it will not decrease the load. I don't see that happening.
There is an interesting observation at a meta level. If these 12 folk are spending a ton of money chasing down answers to queries that are predominantly bullshit, that don't go through recursive resolvers with users, then the interesting meta question is, why don't we take a week to answer them? And it's kind of a thought bubble more than anything else, but it is a question about all this volume at the root, what is it? And one of the ways of pushing back into the recursive set is it does take the legitimate queries to some extent off the table, to some extent. What's left is fascinating. And we have no idea at this point what it is. Oh, and by the way, the beauty about borrowing other people's slides is all the mistakes are his fault.
That wasn't in my stack.
Well, actually, it is our fault because we botched the implementation, right? So we had to fix it. But anyway, I don't speak for ISC, I speak for myself. I have nothing against local root by default, but I'm just saying that it will not decrease the load. That's the whole point.
Eric Nygren, Akamai. I was first
Up close.
Eric Nygren, Akamai. I was first going to ask if we knew what was that growth was from, because it does, but it sounds like the answer is no, because it does seem like one of those cases where it was flat enough but increased enough that there's probably some top set of outliers causing that might be worth trying to go and fix, because if we don't fix those, local root may not help. But I was also wondering how much of this is a problem at the GTLDs, because presumably, like if there's a problem at the roots, you'd think that it's also going to be a problem for some of the for like .com, .net, and some of the other big GTLDs. It's not? Huh.
Like many things in the DNS, raw data is exceptionally hard to come by. So we're reliant on assertions and have no way of actually figuring out if they're right or wrong. And it's kind of difficult to engineer in this environment, I would say, as a meta comment, this is a hard kind of question. It's not all laid out in front of us, unfortunately.
And I think the third thought was, as we go and do the local root, I think it'll be important to think about how do we scale out the distribution, because while 2.2 megas isn't big.
I don't know. I think it's a URL. Haven't the content distribution network guys looked at that problem square in the face?
It's a solvable problem. It's just one that we need to make sure that as we do it, that the infrastructure, that we look at the infrastructure that's distributing that.
I think in web terms, this is a tiny, tiny, tiny problem. But I'm speaking to someone from Akamai. I'm like, talk about teaching your grandmother to suck eggs. I'm like, you guys know volume.
I'm Peter Kordinik. So first of all, speaking of problems, I haven't heard you say that the increase in volume is a problem for the root server operators.
Didn't say that.
No. which is why I said I didn't hear you say that, and nobody else said that. Maybe we should keep that in mind, that there's headroom and so on and so forth. However, of course, it is useful to look at it in perspective. The observation is, or the question is, with those people who would adopt local route, would we address the issues? Because we don't know, right? It's a bit like relying on compliant criminals to show their ID so they can be caught. Here we don't know where this comes from and whether the mitigation is really starting where we
The
are.
normal motivation for someone to do something is that it benefits them. And as a side effect, it might benefit others. The major viewpoint of local route is if you're a recursive resolver, faster, more private, you get benefit. The side effect is that it changes the profile of queries at the root. It seems to be, and I'm guessing, a beneficial change at that point too. But that's not the point. The point is it's better for you.
Well, if I knew that, then I would probably already take care of the junk queries, which we just heard account for the majority of things. My main point actually was the one that was made previously. This is not about the volume in the distribution. You know that we have all this discussion about governance and accountability and blah, 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 blah.
Oh God, you're in the same
including
committee, aren't you?
Yeah,
oh, yes.
no, many of them for years.
Yes, exactly.
But just saying you can get it from the dustbin or anywhere else that is true, but it is nothing I think that the internet can rely upon as a distribution structure. What is this? Oh, it's in the dustbin. Who do I call if the dustbin is empty or if the dustbin serves?
You go back to
out-
incremental queries.
Still, we need something on this distribution structure. So that task doesn't get
But
go away.
by the way, folk in the queue,
Oh,
we have dominated so much time of this IEPG session. I'm going to make my answers less discursive. In fact, I'll try and stick to yes and no. We'll see how that goes.
Jeff, can I add a quick thing to that? So, I mean, on the distribution side, we'd actually spoken to ICANN infrastructure, and they say that they're happy to improve the size of it. And I know also a number of CDNs would be happy to host it as well. But yeah, SoNMD is the important part. Where you get it from, it needs to be safe. Anyway,
I just like to say that queue has been locked some time ago, and please be brief, right, for the sake of time.
Check. Jim Fenton. A couple of questions. I'm trying to understand the growth in root queries. So I'm thinking some of it might be due to the growth in the number of TLDs, and I'm thinking that some of it might be due to a growth in the number of resolvers, like because of people installing pie holes or something like that and doing a lot more local resolution. So wonder if you have looked at the number of IP addresses that the queries come from. And related question, how often does the root change? If you're going to download the entire root zone, how often do you need to do that?
Yes or no? If I'm going to answer yes or no, the answer is yes and no. The really quick thing is caching determines your own freshness of the root. If you look once a day, you're no better or worse off than you are caching queries. That's the first thing. The second one, if we had really good visibility into the DNS, we'd have a much better idea of who asks the root, who asks recursive resolvers, etc. All of that data is so carefully sealed up separately that being an advantage point to see a broad cross-section of the DNS that is reflective of the whole, we've been unable to do that. I'm sorry, there's just no clear data.
Sure, but you could take a particular root server and look at the number of IP addresses and see if that's also growing.
Privacy, all that kind of stuff, really hard. That was a no.
Mark Andrews. I believe most of the crud at the root is actually leaks as a result of bad search lists. Literally. Bad search lists in stub resolvers. So every time you add a new machine, you've added yet another source of badness. So growth grows with the number of machines on the net, not the number of name servers. Yeah.
Oh, so my answer is yes.
Yeah. The root zone gets updated twice a day at the moment. So you download the zone there. If ICANN keeps asking for more TLDs, it'll get bigger. So that's not a good idea we want a small root zone. Yeah.
Yes to all, Mark?
Yep.
Fine.
Transferring down the zone, fine, it works nicely. And negative caching definitely works.
Yeah.
But the more TLDs you have, the more queries you have to make to the root to fill them, because the gaps get smaller.
Really short.
Yeah, please be quick. We're running out of time.
Morning, Andrew Campling, 419 Consulting. So question, do you agree that Warren's draft is far too unambitious and should really be proposing retiring the physical route and moving to an all virtual route?
No.
Good morning, Gianpaolo Scalone, Vodafone. So there are good benefits for privacy perspective, but do you see drawbacks or risks from caching the root in the resolver?
Personally, I don't, because as long as the root zone infrastructure is there, if you can't get the zone, if there's something going wrong, you always fall back to incremental queries. You go and just query one of the 12 root name servers and so on. So what you're doing today will still work. We're not saying junk all that stuff and replace it with a single object. We're saying, as well as that, why not see if the object's around, and if it is, pull it down and use it. That's all. So it's kind of incremental over the top.
And tampering the list? Tampering the list, if the list is corrupted or...
Sorry, I don't quite understand.
If the list is not the original one, so there is some tampering.
It's signed Zone MD, and quite frankly, you can get it from, I still say the garbage can, as long as the signatures say it is current and the entire contents are valid, there's no crap in there, it's the root. It's the real root. What's your problem?
Okay.
We're through the queue. Over to you.
Yes. Thank you very much.
Fascinating
Jeff.
questions.
Okay, Shane, would you like to request the control, or you like me to move your slides?
I guess you can move them.
Okay, let me load
so
your
I don't
slide.
screw it up.
Okay. Oh, come on. Okay. We continue with DNS with some IPv6 topic added, despite Warren not believing it exists. Okay.
All right. Thank you. So hi, I'm Shane Kerr. If any of you were at the Right meeting recently, you've seen a lightning talk version of this. This is slightly padded out for my esteemed audience here. And basically, it's what the title here says. We're going to look at IPv4 versus IPv6 for authoritative DNS. Next slide. So the reason that I started this research was that like NS1 was a startup 15 years ago or whatever. And since the very beginning, it did IPv4 and IPv6. And at one point, our professional services team was asked about the performance of our IPv6 edge. And they just wanted to answer, it's great. And I said, no. We can measure this. So let's do that. And so that brings us to the next slide, please. A measurement. So I want to do a very simple measurement. I made a zone with only A records in the NSR set. And then I used Ripe Atlas, 1,000 random probes. And then I repeated the same query. The idea there is to get as much of the hierarchy in cache as possible, so that you're only measuring that last step between the recursive resolver and our edge. And it's not perfect because people that are running clusters of resolvers may not have the same caching behavior, but it was just an attempt to make things more fair. And then I did basically the same thing with an IPv6 only zone with the same probes. And to make an IPv6, I used quad A records only. And I checked it with Zone Checker and it complained. So I figured it was probably pretty okay. And you can see there that, and I have an open action to fix this report on the zone checking because it doesn't complain when you only have IPv4 address, but it does complain when you only have IPv6. I'm gonna suggest recommend a fix for that. Anyway, that's the idea. We're just querying two zones, IPv4 only, IPv6 only. Next slide, please. And so this is the results. The queries actually time out after 5 seconds, but that gives you a long tail of pointless data. So I capped it at 500 milliseconds here, bucketed it, and you can see the hideous blue IPv4 and the beautiful IPv6 orange lines there. And what you can see if you look is that the IPv6 leans more to the left, which actually means it's a little bit faster. Great. Next slide, please. Yeah, so it's very, very close. I'll be fair. The first time I ran the experiment, I had to like fix a few things, and it was like 3% the other way. So it's a little fuzzy. And you also, if you remember on the last slide, that said the average. So what I did was when a Ripe Atlas probe starts, these are probes that people run in their homes or in their offices or ISPs or wherever. The intention is for them to look like end users. And when a probe starts up, it gets the addresses of the resolvers from the network somehow. I guess DHCP or router advertisements, maybe DHCP6, I don't really know. Anyway, it gets a list of resolvers and it checks them all when you ask for it to use the local resolvers. Now, it's a bit tricky because as far as I know, there's no standard for how a client is supposed to pick between the resolvers that it gives. So you can imagine a whole bunch of different behaviors here. Probably a lot of them just start with the first one, and if they get a serve fail and they move to the next one, they may then stick with the second one. They may go back to the first one. They may use some sort of RTT-based algorithm, whatever. We don't know. So what I did for this next, I took the exact same data, and that's this slide that you're seeing here. And this slide is the same data, but only the fastest result of all the ones that were returned. So you'll see you have like on the far left, like the 10 millisecond or less responses. You see a lot more of them. Yeah, people are commenting that there's a bunch of other heuristics and algorithms people can use. But anyway, so somewhere between that previous slide and this slide is probably the response times. So if you go to the next slide, please. So what do we see differently? Well, like I said, the fastest probe is much faster. IPv6 is not as much better from this view, but it wasn't that much better before. And we don't really know what the clients are doing. So fastest probe might be more accurate, or it might not be. Hard to say. My intuition is it's probably closer to correct than the average of all the probes. Anyway, next slide. Okay, so that's not really important for the talk. What's actually important is that when I went to go look at the raw data, I was just clicking through all the pages that Ripe Atlas provides you. It has great graphical tools and things like that, which I never use. I always just write some scripts to analyze the data. But it was only on the very last page listing all of the probes for the measurements. So you can see here, we didn't actually get 1,000 probes, though we requested them. We got 967, right? And of them, 97% got the correct measurement for IPv4, and 96% got the correct measurement for IPv6, right? So it's basically the same. And this is a really surprising result to me, at least, because the end users I made no effort to pick IPv6 where host. I did nothing. The actual queries themselves were made over IPv4 to the resolvers from the probes. So what this means is that just picking 1,000 people on the internet at random, IPv6 is basically just as good as IPv4, which I found very surprising. And so my immediate thought was, fantastic. We can sell our IPv4 addresses back. We don't need them anymore. Great. But of course, and this is kind of where I left the presentation at the lightning talk at the Ripe meeting. But I started to look a little bit more since then. So next slide, please. So this is the view from Quad 1, which is run by Cloudflare, a public resolver. If you have a PeeringDB account, you can log in and see requests to your AS. And that's what this is. So this is RAS NS1s. And so looking at this, I have a mouse over there. You can see that we get 49.34% over IPv6 and the rest over IPv4. So this is awesome. This is what you want to see, right? So we don't treat our network separately. We treat them the same. We try to deliver the same perfect quality for everything. And so this is exactly what you would expect, right? So if you have resolvers that are doing round trip time measurements and trying to pick the fast resolver, they will basically, if you're doing things right, end up with a 50-50 split. So fantastic. Next slide. Great. Yeah, so IPv4 and IPv6 are the same. We're not losing IPv6 queries. So again, are we really ready to be done with IPv4? Next slide, please. All right, so I couldn't stop myself, and I kept digging, unfortunately. And this is our actual data that we're pulling from our edge. And you see we have it broken down by protocol family here. And unfortunately, we get a lot more queries over IPv4 than we do over IPv6. Now, this makes me very sad because, as we saw before, IPv6 queries work fine. From the Cloudflare point of view, with a well-connected resolver network, everything's great. So this is a little bit of a conundrum. So next slide, please. Next slide, please. Okay, great. So looking at that, we see about twice as many IPv4 queries as IPv6 queries. Next slide. All right. So at this point, the data runs out, and it's all hand-wavy and guessing. So from the point of view of Cloudflare and NS1 Connect, we both have good IPv6 edges, and it makes sense that we'd have parity of queries, which is what we saw. Again, looking at the RIPE Atlas results, RIPE Atlas sits in location, like the probes sit in locations. These probes they're not like people driving around and picking random places on the internet to put them. The RIPE NCC hands physical probes to people, or people who want to can download and implement a, oh boy, I'm too loud, sorry. Anyway, people can download it, run a virtual machine or whatever. But basically, RIPE Atlas probes are sitting in places where people care about their network and are usually going to have decent resolvers. And if they don't, people are going to find ways to improve the situation. Not in every case, of course, but more often than the average person on the internet. And now if we compare that to our own data that we've collected it from our edge, most of our customers are enterprise customers. That's our target audience. And their customers are probably, in many cases, also enterprise customers. And they're using, Windows Active Directory setups, which are running on an old Windows 2000 machine, and barely have working IPv4 DNS, and the chance of having IPv6 is basically zero. So it could be that the difference comes from this kind of disconnect between the first two cases, which is sort of like, this is the internet at large versus our customer base. Now, I don't really know. I haven't done the analysis on that data to try to figure out why we're getting so much IPv4 queries. I'll probably do that in the future, but that hasn't been done yet. Next slide, please. All right, so now if one did want to consider the case of how can I get to a perfect world where I don't need the IPv4 to run an authoritative DNS server, how would you do that? And I think there are sort of incremental steps that one could make. So one simple step, for example, could mean you might just have fewer addresses, fewer IPv4 addresses than IPv6 addresses, which would naturally sort of gently push people towards using IPv6. We could also offer an IPv6 only edge for customers who don't need IPv4. I don't know if such customers exist. I think I'd have a hard time explaining to our business people how that would make us any more money. We could also give incentives for people to actually use that edge. But again, I don't think it's like running our IPv4 edge at this point doesn't cost us a whole lot. So the business case is not there. And all this kind of pushes to the last slide. Next slide, please. Which is how you get to the point where you're not using IPv4 for your authoritative DNS. Right now, I don't think there's a lot of business reason for it. You don't need many IP addresses to run DNS, and those IP addresses will answer like literally millions of zones and billions of records. And it's not a huge expense in that context. Having an option though, like I was talking about on the previous slide, even if it wasn't heavily used, could provide some data about the usability of such an option and things like that. And I think there could be real value in IPv4 only networks. For example, we're a managed DNS company. We have a hosted DNS, and that means a lot of our customers share IP addresses with other customers. Using IPv6, you could have a much better you could really effectively isolate customers from each other in ways that are not really possible in IPv4. So it's not just about loving IPv6 and wanting to move to the future. I think there could be real value here that we haven't explored yet, but maybe it can be done. Anyway, that's basically it. And any questions, anything like that?
I'd like, sorry, I just want to remind people that just for practice for the week, please try to use Miteco client to join the queue. The chairs, yeah. Thank you for everyone who is doing this already. I'm just a gentle reminder. I can only count to 2. I cannot keep track of people joining the queue without Miteco. Sorry.
Okay. Tom Hill. Thanks very much, Shane. I saw this at RIPE, and then I appreciate the extra bits you've added on the end. One of my big bugbears about this at the moment is that I'm looking at this from the position of a very large ISP, and many of the other ISPs, especially in the UK, started to use CGNAT for IPv4, various other types of translation. I feel like as this increases and as this usage increases, I really hope that we're continuously looking at the difference between V6 and V4 in these environments, such that we can plot the demise of the quality of IPv4 over time and shout about it very loudly if for nothing else, and for those enterprises who say, what's the point? I don't, IPv4 works fine. So thank you for doing this. Perhaps you may consider continuing to do it. It would be really good. Appreciate it.
Yeah, for sure. Like I said, I definitely want to look into some of the reasons why we see twice as many V4 as V6 queries. So I'm planning on doing a little more research. So for sure.
Hi Shane, it's Joe Abley here again. I was a bit depressed to see your checking tool said that a V6 only name server was no good, because I remember Ed Lewis telling stories years ago about the .biz name servers. One of those was V6 only, and that caused everybody to complain that it was broken because you couldn't ping it. I had one of my personal domains under a CCTLD, not the one I use right now, was had a V6 only name server, and they used to call me because the zone generation scripts would break every single night and have to be manually restarted. And they asked me if I could add a V4 address, and I declined. But I think this is protocol grease for name servers. I think we almost need to make it best current practice that every zone should have at least one name server that is V6 only, in order to exercise all these bugs and make it less likely that these things are treated like an error. And if we did that, it would also have the effect of perhaps having a measurable effect on the amount of V6 traffic we see at authoritative servers.
That's interesting. I mean, I think I don't know. So part of the reason I wanted to run the original experiment was to see what happens, right? And so I feel like we actually kind of did a little bit of greasing just by showing that everything seems to work for V6 only servers. I'm 100% sure that's not true, like for every TLD that you sit under, for every resolver that you use, and things like that. But I think it's not. I'm hoping it's not as grim as it was 20 years ago when Biz had a IPv6 only server.
Job Snyders, not a lawyer. Can you go to slide 16, please?
Oh dear.
So this looks awfully similar to a legend instruction, and I'm very unclear on the position of the IESG on legend instructions embedded in presentation materials withstanding to our planning process. So if the two chairs could maybe prepare a statement for the next meeting on how we should interpret this, that'd be great. Thank you.
I mean, I'll have to go have a look and try and remember. As far as I remember, what we'd heard from the IETF legal counsel was these things don't do anything, but and I understand some presenters are kind of required to include them by their corporate people. And so I think it's like, which I realize is, clearly I'm not a lawyer. This is not legal advice. Consult your own lawyer. I'm definitely not your lawyer. But yeah, I mean, we'll try see if we can check again, because point taken though.
Mark Andrews, ISC. Where's job? Okay. One thing you need to remember is the IPv4 only sites can just forward to a dual stack server. Bind actually has a command in its config file, which will actually tell you where you can tell it to go and fall back to a dual stack server if you're trying to reach a IPv6 only zone. And just pointing it at one of the quad servers is a great solution for that. So it is just dual stack servers, and you just put the IP address in there, and all your IPv6 only servers or just zones will work. Okay.
Thanks, Mark.
Okay. Any other questions? Okay, great. We are almost back on time. So now a bit more about IP. Okay, let me get the slides. Change that. Do you remember what I need to do for this?
You need to have it plugged into your laptop.
No, there was a way to delegate something, and then it would work, right?
You still need the clicker thing.
I need to delegate it to clicker or something. Where is the clicker? Oh, yeah, clicker.
Is somebody in the room good with computers?
Okay, yes. Okay, let's see. Oh, let's try this. You see, I'm practicing. No? No?
You have to delegate it to the user that is clicker user.
Yes, it's what I did. I gave control to clicker.
I think I didn't turn it on.
Physical layer.
There we go.
I see.
Turning it on helps.
Okay, timer.
I can't make it in 45 seconds though.
No, I'm working on it too. Go on.
Technology is hard.
Hold on. 20 minutes. Yes.
So, is it on?
What?
The microphone. It's on. It's working. Is it working? Amazing. Yes, wonderful. So after we now had some DNS, some v4, some more DNS, and some v6, we're now going into some NAT and NAT64. This is somewhat joint work in several parts with my colleagues Zilan, Taha, and Anya. And well, I'm of course Tobias. So how did this all start? So at IETF 122 at the IEPG session, I had this talk about these DNS IPv6 measurements we did. There was a presentation at 123 in DNSOP. There's this funny paper about how I learned to stop worrying and love IPv6 and measuring the internet's readiness for doing more v6. At IEPG at 122, there was also Jen, and Jen did what Jen usually does. Jen asked, but what about NAT64? So, to quickly recap, what did we do? We took the Google crooks, top 10 million, tried to resolve them, IPv4 only, IPv6 only, dual stack. We did this using a minimally covering an asset. So for all these domains, we got DNS sets. So we picked domains that each of the DNS sets would be hit once. We did that for DNSSEC enabled and non-DNSSEC enabled domains. And then we implemented various MTU scenarios. So standard 1500, 1280 on link with broken parse MTU, with working parse MTU, and 1280 on parse with broken parse MTU discovery. And the idea then was, let's just do the same thing if you are doing NAT64 in between. Should be easy. So during 122, despite the somewhat difficult latency situation, I did what would do. I added 4 measurement hosts. I set up 4 net64 hosts. I did measurements. And I got kind of annoyed emails about me sending an awful lot of TCP resets. By the way, thanks and apologies to Sven van Dijk and Gert Veren from DNS Belgium, who were the ones who were suffering a bit under a little bit too many TCP resets. Question, of course, is why? Did I run out of state table? Is OpenBSD just slow? I figured that I would solve that like usually academics do. I would hand out a thesis and let somebody else do the hard work. So this is then what the first part of this is about. It's a bachelor thesis together with HTWSR at the Max Planck Institute for Informatics. We try to benchmark like the standard open source net64 implementations, Tiger, YOL, OpenBSD. Did this using the base case of what we just saw, so an MTU of 1500 with the DNS measurements, looking at especially the timeouts, and small and big packets for just throughput tests with IPerf. So, problem is before measurements could start, there were some issues. Like students set up everything worked. I tested it from my machine at home, was like happy, like go for the measurements. Zilan went for the measurements, and the result was an awful lot of not working stuff. So I tested it from my home, like manually, making TCP connections through it, and it worked. But from the measurements host located at the same machine, and that's actually what we see on the, from your side right here, and I think I do have a laser pointer, yes. So we had like one VLAN with the net64 and the measurement host in 1/64 with the pref64 routed by the local gateway to the net64. In that setup, the net64 would just immediately send a TCP reset or a UDP port unreachable for UDP. Of course, to aid debugging, ICMP v6 worked fine. So that was a bit odd. So first course of action, maybe this is some form of weird parse verification, like it is basically an on-link address, but it comes from the router. Let's just drop it. So first thing to try was setting a direct route to no avail. Same issue. What did work though is if that second, like the measurement host, would move to its own VLAN, still on the same hypervisor. But for some miraculous reason, then there were no TCP resets. We still don't really know why and how this has happened. If anyone has an idea, please, we are happy to share PCAPs. We try to do the most reasonable thing in that situation, which is assuming that it is something which has to do with offloading, but disabling offloading also didn't help. So weird. Anyway, after this little issue was solved, we could actually see the net64 measurements. And with IPerf, there is not really that much performance impact of the net64. Throughput, of course, a little bit better for like the native case where you don't have to go through a net64. Of course, offloading makes throughput generally better. And of course, small packets give you less throughput, higher PPS. If we look at the DNS measurements, offloading seems to introduce more noise. So, so it wasn't me. Thank you to our new Meet Echo guy. I hope the online people did understand anything. Anyway, so what we saw with the DNS measurements is that throughput is indeed better without offloading again. Like we can get a bit more through, we peak a bit higher, but the noise gets more. And OpenBSD is kind of on tie together with Tiger. For some reason, we get more timeouts with YOL. So what we can kind of conclude, using OpenBSD in the measurement setup kind of was fine. So I probably ran into the same bug issue, which I now solved by having these virtual machines on different hypervisors. So the next thing to evaluate is then work with Taha. So at 121, Peter was like, well, having something we could use to evaluate like DNS servers, which we are developing, would be kind of cool if we could like see all the oddities out there. And that idea was the minimally covering in assets. Still, in these minimally covering N assets, we might get still some overrepresentations. For example, Amazon has like all these AWS DNS name server sets. So we have like a ton of NS sets which have like 4, 5, 6 domains. And well, if we would aggregate them, Amazon would be like really, really big. But this way, they are still dominating the minimally covering an asset. Cloudflare, similar thing, not as bad. So the question is like, if we are using minimally covering an assets, does it in some way influence our measurement data on this? So we actually did like a full measurement. So instead of like using the minimally covering an asset, we would just like test all domains. And then we would calculate what it would have looked like with a minimally covering an asset. And we would also rescale that. So if we have a minimally covering an asset, if we would multiply the data we got based on how many zones are on that server, what would be our results? And also what would happen if we slice it differently. So if we start aggregating all these Amazon name server set things to one. What we found was a little bit surprising. So this is a nice radial plot of all the experimental situations which we are measuring. And on the lower left here, you do see IPv6. And in IPv6, the difference between the minimally covering set and the non-minimally covering sets are a lot smaller. What you also see is that IPv6, like the blue line here, is the full measurement. For some reason, timeouts are higher for v4, if we're doing the full measurement, than for v6, while if we then use the minimally covering set, IPv4 all of a sudden looks better than v6. So it seems like this methodological choice, which we used in also our paper, actually made v6 look worse than it actually is. And remember, back then, there also was the conclusion that v6 is not looking that bad at all. If we do the scaling, then we actually see that like our scaled sets for especially v6, and this is for zones without DNSSEC, are getting pretty close to what we would see if we would have just done the full measurement. For IPv4, though, there is still some ground to make up. The other important thing to note, though, is that the behavior like in between classes, like the relative matching of the impact of having like working path MTU discovery, a certain MTU, etc., is kind of staying conserved, even though the absolute values we observe for timeouts change if we do the scaling. If we now move to DNSSEC, it of course gives us a lot more noise if we have broken path MTU discovery on path and an on path MTU break, which is kind of to be suspected because even TCP on IPv4 is not that happy with MTU black holes. But like it pushes through, but for some reason so does IPv6. The impact of that is kind of over-amplified in the minimally covering set because it kind of makes sense if you just have like one zone there that is suffering from the MTU black hole and then prevents resolution. That just is a bigger share of the overall set of zones or NS sets. And we again have this IPv6 looking worse in the minimally covering set thing. And for scaling, especially our over-amplification, still to a degree remains there, but we also have that in like the full measurements. So it's most likely a DNS set thing because of the larger responses required, especially for DNS keys. And we still have the underestimation of v6. So quick recap on the minimally covering an asset impact. We can actually save a lot of time with that. So I think the numbers are a little bit small to see, but our full set would be like 3.5 hours roundabout to measure. With a minimally covering an asset, we can get that down to round about 30 minutes. So a lot easier to get like a relatively interesting and representative sample. And that is with 400 queries per second. We do have a small set, so around about 1% of NS sets that in the full measurements then returned mixed responses. So various zones would give different R codes. A major portion of that was NX domains because over time, of course, zones go NX domain. But there were also, for example, NS sets where only the first zone we tried to resolve would resolve successfully, and the remaining zones would all run into timeouts. If we scale minimally covering NS sets, we can actually get relatively, well, we can get closer to what we would get from a full set. But the most important bottom line is if we want to use this to look at like how the DNS works, the relative proportions between the different classes remain the same. So it's kind of a good looking glass to get a feel for how these things work. With all that said, let's get to Net64. So what we see here is basically the same kind of plots for our DNS measurements. And the first one here is dual stack resolution with, just a second, yeah, with IPv4. This is IPv4, just a quick, yeah, no, this is Net64. Sorry, plots are a little bit fnolly. So we see with 1,500. The kind of expected timeout bubble here. As soon as we have DNSSEC enabled and we do have broken path MTU discovery or an on-path MTU break, what is kind of interesting is that broken path MTU discovery for an on-link connection and on-path kind of look similarly bad for Net64. Because usually in like the other experiments, it would look better than an on-path MTU break because, of course, you do get MSS information because like it's on link 1280, so you know the MSS that it should have. And when you then do a TCP fallback, your success chances are higher. That does not seem to be the case if you are behind a Net64. Interestingly, dual stack resolution also heavily suffers, like similarly heavily, from path, broken path MTU discovery with an on-path MTU break. And there's a similar baseline in timeout. So if you compare this here for 1,500 MTU with working path MTU discovery, it's like 0.05% timeouts, and that's somewhat similar if we do dual stack resolution. And if we compare the two, we actually see like these two portions really nicely highlighting out, which is that 1280 on-link MTU break with working path MTU discovery is a bit worse with Net64. If it is without path MTU discovery on link, it is a lot worse. And if it is on path without path MTU discovery, it is again a bit worse. So bottom line, we saw that offloading is a bit of a story full of misunderstandings. Minimally covering an assets kind of work to do fun stuff and fun measurements if you want to get a broad perspective and don't want to send too many queries. And if you have a choice and you can decide between like doing a native query or piping it through some XLET or something, just try to go for the native query. Questions? Great. So we can all roll out V6 for DNS, and hopefully then you don't have to hear Net64 talks anymore. Thank you.
Thank you very much. Okay, and the last presenter for today is busy typing. Okay, I still need to. Yes. So do you want a clicker? Sure. Okay, hold on. Let me. Few seconds.
Testing 1, 2, 3. Yeah.
I will give you control in a second. Okay.
Ready, set, go. Good morning, everyone. Thank you for attending my Sunday morning sermon. I am here to talk about RPKI. Are you a believer?
Amen, brother.
And specifically, I want to talk about how we distribute RPKI data from the origin, the certification authorities, to the relying parties. Oh, I have 3 minutes, so I'm gonna rush. Oh. Oh, yeah. Next slide is. Do I need to?
No, not me. Hold on.
If there's one thing I love about the IEPG meetings, is they're so well organized.
It's the first meeting of the week. You need the patience. Why? Did we turn it off again?
On the side. Job, you have to turn it on.
Okay.
Okay, we're not learning as fast as we should.
So as I said, on the airplane from Amsterdam to Montreal, I went through some data, specifically of October 30th, to give you a bit of a sense of what the shape of the RPKI distributed database is and what RPKI validators have to plow through. So at the start of October 30th, at midnight, 00 UTC, the total cache was composed of nearly 500,000 objects. These objects have a median size of about 1924 bytes, or say 2 kilobytes, and every 2 seconds, every second, 2 new objects appear somewhere in the RPKI. The day ended with about 3,000 objects more than we started, so this means that there were some changes in the route origin authorizations. But it also means that a lot of the objects simply replace older versions of objects and are reissuances with new validity windows. In raw form, the data set is about 900 megabytes. And if you compress it, you get about a 50% reduction. So it doesn't compress super well. And there's currently about 5,000 validator instances observable under the RIPE trust anchor, but we don't know if that is the full set of validators on the internet. The update rate can be shown in this beautiful GNU plot logarithmic exercise. I said 2 per second, but there always is a peak around the top of the hour because it seems that a lot of certification authorities have cron jobs that fire at the top of the hour and pump out fresh data. Now, the hand we were dealt with is essentially star topologies without redundancy. Every RPKI certification authority will use one publication server, and that publication server has all the data for its constituents, and every relying party must fetch from every publication server. You have multiple relying party instances per autonomous system. So even though it at first glance seems there's a lot of duplicity in the system, there's a lot of one-to-one connections that cannot supplement each other. So for instance, RIPE's publication server does not contain data related to a PNX RPKI operation. I cannot fetch a PNX data from RIPE's server. And the consequences of this are that the SPICE doesn't flow as fast as it might be able to flow. And particularly with data revocation, this is noticeable because the way the RPKI works is that all the caches in a given autonomous system must have observed a revocation before that revocation is enacted on. Other issues we see is that globally, some publication servers will just congest for a period of time. So for instance, Afrinix RPKI server was poorly reachable for a number of weeks last year, but they are not the only ones. And there is problems in a very hyper-local scope. So for instance, between a given publication server and a given relying party instance, that particular path might be broken. And that means that that one instance cannot reach that one publication server, but it cannot get the data from elsewhere. So that one instance is either going to experience delays in acting on new information, or it might be missing information. There are two mechanisms through which we distribute RPKI data at present. One of them is rsync, and there are a number of concerns with the scalability properties of rsync. The rsync protocol, in a nutshell: client and server exchange a full list of all the files that are present on either side, and then they, on the fly, calculate what files should be transferred to the client to bring the client up to date. So it's really cheap to transfer the difference once you've calculated what the difference is. But calculating what the difference is between the client state and the server state is pretty expensive. And this makes rsync suboptimal for frequent synchronization. So as we do in the IETF, we observe a problem and we invent a new standard that surely is going to fix it all. So enter RRDP, the repository Delta protocol. The RRDP design is very different from rsync. In RRDP, all the repository mutations are written into a journal. The client downloads this journal in chapters, replays the chapters one by one, and then is up to date. So again, on paper, this looks super efficient. A problem, however, is the clients ahead of time don't know what they are downloading. So this means that they cannot skip downloading information they already have because of the way that RRDP encapsulates the actual data. And this also means that clients download data that's been overtaken by events. So if you have a system that is changing a ROA every 10 minutes and the client is synchronizing every hour, it means that the client must download the 5 previous states and cannot avoid downloading those. Or phrased very differently, you tell me, hey, Job, I want today's newspaper. I'm like, that's cool, but you must download yesterday's newspaper. And the client is like, but I have absolutely no interest in yesterday's newspaper. I'm like, haha, you have to. And another issue with RRDP is that many paths in its, if you consider it a finite state machine, lead to excessive retransfer of data. And we'll cover that a little bit more. So I took some machines and I used a PF, but you can do the same thing with IP tables, and you can match on data originating from a specific Unix user. So I created Unix users, one that does a process with rsync only, one that does a process that first prefers RRDP and then falls back to rsync. And I made some measurements, like how much data are these things consuming in a steady state over the course of some days. And the handshake is how much data is burned without actually transferring RPKI data. So this, for instance, happens if both client and servers are perfectly in sync, and the client just wants to confirm, am I still in sync? So you can see rsync is a pretty expensive API call. It consumes 4 megabytes just to figure out, are we in sync, yes or no? And RRDP is a lot cheaper in that regard. But if you synchronize every 15 minutes, rsync is not a cheap way of transferring the data. RRDP is way cheaper. But if you synchronize every hour, RRDP performs quite bad and rsync performs quite good. And this is because with rsync, the client and server go through a dance where you can immediately jump to the latest state. You skip over the intermediate states that have been overtaken by events. Whereas with RRDP, you must download yesterday's newspaper in order to arrive at today's newspaper. So RRDP, I would say, is very salty. If the connection times out to fetch a delta, like one chapter, which is a small file, then the protocol tells you to download the full snapshot of the entire repository. So if you have a congested server where like one fetch didn't go according to plan, you're going to hit that congested server with, well, you refused to give me the 100 kilobyte file. I am now going to request a 100 megabyte file. Screw you. And this, of course, is not great. Instead of exponential back off, we have an exponential fist in the face mechanism here. Now, people over the years recognize that rsync and RDP are, we need to do some fine tuning to squeeze the most out of these mechanisms because they are the mechanisms that we have. So some tricks exist. For instance, RIPE NCC packs as many prefixes into as few ROAs as possible. And this system behavior results in quite efficient encoding of the data, which reduces the data sets, which reduces the problems resulting from rsync and RDP. We came up with the mechanism of deterministic timestamps on rsync servers to reduce superfluous data transfers. RDP came to be, which is in a lot of circumstances is a little bit more efficient than rsync. RDP is HTTP based, so we get niceties like if modified since and HTTP content encoding compression, but it's not enough, I would say. So the power balance is that a publication server chooses how they make the data available. So some publication server in a small country that starts with a J and ends with a pen might decide that their publication server obviously is going to be hosted in Japan because that's where their constituents are. And this thinking pattern, there's nothing wrong with that, but it's not optimal for relying parties that are on the far side of the planet from that perspective. And as I mentioned before, clients cannot choose where they fetch the data in the current system. If a CA designates that the subordinate products are going to be at that server, then that is where the client must connect, regardless of local network circumstances. Now, RC 7115 highlighted a different way of thinking where it suggested that caches can prime or feed other caches. And replicating data from cache to cache would be a mechanism to reduce the load on the global RPKI. And that is what we're going to do. Enter ERIC synchronization. ERIC synchronization is a new data replication system that is intended to perhaps in the long term replace either rsync or RDP. And it's composed of a few concepts. It uses Merkle trees, content addressable naming schemes, concurrency control using monotonically increasing sequence numbers. It's based on HTTP, and it introduces a new player in the ecosystem, something called an ERIC relay. So in the previous model, we had clients, the relying parties, and servers, the publication servers. And in the new model, there's an intermediate network element, an ERIC relay that sits between the clients and the origins, the publication servers. A ERIC relay aggregates data from multiple publication servers and makes that available to clients. So there's not a one-to-one mapping between relays and publication servers. A single relay can contain data from multiple publication servers. And in relays, multiple transports can come together. So a relay on the backend might be fetching through both rsync and RDP, and then present the resulting data in a merged format to the clients for consideration. So in that sense, they are spoolers. Relays can synchronize to other relays, and clients can rotate between different relays because of the nature of the content addressable naming scheme. So every request can be sent to a different relay, and you would still arrive at a usable outcome. Relays are operated by third parties, so they are they don't need to be operated by the publication server operator or the relying party operator. It can be other entities. If we compare rsync and RRDP and ERIC, there's a few interesting characteristics that I want to highlight. In the ERIC synchronization protocol, the client jumps to the latest state, just like you have with rsync. So intermediate states that were overtaken by events are not forced into the client like with RRDP. The client will only download what changed. And this is very different than RRDP and makes it more similar to rsync. The content is static. It is not calculated on the fly. So in that sense, it's a little bit like RRDP. It's HTTP based, so we get HTTP content encoding, compression, and if modified since, but also new technologies like compression dictionary transport and all the niceties that come from using HTTP. It's very light on state because the client calculates its local Merkle tree, and then it compares that with the Merkle tree that the relay is offering. And by walking through these Merkle trees, a client and server can very cheaply and efficiently discover, is there a difference between my local state and the remote state? And where is that difference? What is it that I should download to get up to date? And this property of not having a session between client and server makes it so that the clients can rotate between different relays because they don't need to establish a session with the relay like you would have with RRDP. Now, in other words, it is efficient, fast, and cheap. I think I finally did it. We have a RC 9025 compliant protocol. For us that like visualizations, this is a schematic overview of what the future would look like. On the left side, you have publication servers that can be reached through different means. Maybe they're rsync only or RRDP only, or reachable through only v4 or only v6. Then there's ERIC relays that put in a lot of computational resources to try and fetch data from those origins. And they present the data in a more efficient format to the relying party. And a consequence of this is that if somebody is hosting their publication server on a dinky DSL connection in rural Indonesia, the moment one ERIC relay manages to fetch fresh data from that hard-to-reach publication point, it sort of hits the highway and is on a fast path to global distribution. So the relays, some of the burden is transferred from the publication points to the relays, but the relays have been designed to be efficient. So it's not a one-to-one, like the cost of running a publication server is 10. So we're moving 9 out of 10 burden to the relays. The relays are more efficient. So we reduce the burden by 9 on the publication server, but it increases the load on relays by, say, factor 2 or whatever. Like, it's not merely reallocating cost, but it is also reducing cost. And some preliminary measurements are that the ERIC synchronization protocol is better in all circumstances. And I think this is a really nice property because from our earlier table, it was clear that rsync and RRDP outperform each other in different scenarios, but the relying party doesn't know upfront which scenario is going to happen. So they cannot pick a proper synchronization technique because they lack information. And with ERIC synchronization, whether you're on a short schedule or a longer schedule, it consumes less bandwidth per synchronization attempt compared to the other protocols. So this is why ERIC synchronization is cheaper. It consumes less bandwidth, which means less IOPS, less everything. Now, next steps. Is this real? I've put up a relay at relay.rpki-servers.org. This is globally anycasted, and I put a note specifically in Australia for our Australian friends to see if they can get fast performance out of that. There's one in South Africa as well, and in Europe and Asia. So I would invite people to take a look at this protocol and experiment with this particular instance and see if they get good results. Based on those experiences, we update the ERIC draft and iterate on that. And then at some point, this maybe can be adopted by some working group, and the sausage machine continues. Now, the end goal for me is to get deployment enabled by default in relying parties, because I think this type of protocol is an upgrade compared to the current approach. It has a number of features, such as the client and the publication server no longer have a direct relationship, and this makes it harder for publication servers that are of an adverse nature to target specific relying parties, because the relying parties are now hidden behind the relays. But yeah, it's a very different approach than what we've been doing so far. Another thing to consider is when RRDP came to be, each and every publication server operator needed to enable RRDP independent from other operations enabling RRDP. So in an ecosystem with, say, 80 participants, that means that 80 entities need to plan enabling the new protocol. The ERIC relay mechanism sits between client and servers, and this means that if a client supports the ERIC synchronization protocol, suddenly it can access all servers through that relay without the original servers having made any changes to their setup. So I think the deployment story is very different compared to dual stacking between rsync and RRDP as we've done previously. But yeah, we'll have to see how that goes in practice. So the big question, of course, is who's going to foot the bill? Are we going to go Dutch on this, or shove the bill towards rich entities? And some entities have expressed some very tentative interest to operate globally reachable relays, and amongst them is one RER, but also two cloud providers indicated some interest to explore this. And a way of thinking of ERIC relays is to consider them like the public resolvers that try and give good service if local circumstances are maybe not as good as they ought to be. And I think we don't need a lot of relay operators. I think if the ecosystem ends up having 4, maybe 5 relay operators, that should be good enough. So we'll see how this develops, but we don't need many relay operators, but the relay operators that do step forward should really commit to running relays for multiple years, because eventually I want to hard code relay addresses in the relying party implementations. And that is the end of my presentation. We have lots of room for polite discourse and arguments, back and forth, ideas. With this, I open up the microphone. Rudiger, we have 20 minutes left, so if you want to make a brief statement.
Looks nice. Actually, the point that for me, when you said you wanted to code the relay into the hard code, and that reminds me something like 30 years back that people were telling, well, okay, having the NTP servers hard coded is haunting a decade later. don't do that. Or
Don't tell me what to do.
well, okay, actually DNS names hard-coded are kind of fine, but
I mean, RC, so there was some previous research on new mechanisms to distribute RPKI data. And Randy Bush and Rob Austin did some tests using BitTorrent. That was not as efficient as this is, but reading the experiment notes is very illuminating on how do you even think and measure different transports for relying parties. And they noted that one of the issues is the discoverability of the new mechanism that relying parties can use. In my mind, making the relays discoverable through the RPKI itself is perhaps not optimal, because then there's a bootstrapping issue. And if we carefully consider like what relay operations can truly exist for years on end, what organizations are able to engage in such commitments, and then based on that, consider coding in relay addresses, kind of like root addresses are coded in, is an option. But there's many ways to distribute configuration, and hard coding is one of the mechanisms. Maybe we'll come up with something else. But we'll see how that goes. You want to use my microphone? Yeah. Maybe you should turn it on. Like there's a button on the side.
I did not turn it off, so it is on.
There is a logic error there, but
I think it went out of battery.
It has been on for an entire hour and 40 minutes. So.
It is now on, I think. Because now, like now you hear me again, right? Okay. So I would like to echo what Rüdiger said, that hard coding things can make for interesting experiences. And I think the past roughly 12 months provided the idea that even organizations we might perceive as being very, very long-term stable might not necessarily be that long-term stable. But I think that the overall idea might work with like an IANA assigned block and like some form of governance that makes sure that this block is then anycasted for any relay node and stuff.
You're suggesting to add another committee.
The committee of Eric RPKI relay operations. Sounds fine to me.
All right.
Or you just get the prefixes and get them blocked by IANA so they don't get sold off to like whoever likes to do IPv6 trade, IPv4 trading, and then you can actually hardcode those addresses. Or you do v6 only. Anyway.
So to clarify, the ERIC relays can just run behind DNS hostnames. So that is a level of indirection that can be useful. If you embed it in software updates, then in the RPKI, I think most validators get updated at least once every 2 years, like 80% of them. And relying parties verify the data they obtained from a relay. So even if a relay is serving trash, then the relying party will be like, okay, well, you're sending me garbage. And lastly, in this particular protocol, a relay cannot only discover a client cannot only discover that the relay has different data, but it can also see whether the relay is offering newer data. So if a relay goes still, like its updating process just dies, but the service is still online, then it will be serving still data, and clients will ignore all of that, and they will not fetch it. So it doesn't cause issues to a large extent.
Yeah, just one more thing. Like as a security person, I think the assumption that people do update software might be brave.
Lancheng. Async and IDP have these problems, and I see the Eric relays still use async and IDP to fetch data from publication servers. So if the number of Eric relay is large, I think the problems may still exist. So I do agree with your suggestion that we don't need a lot of relays, we don't need a lot of relay operators, but I would also like to know, how do you think about this problem? Is this a big problem if the relay if we only have a small number of Eric relays?
I mean, as understanding the size of the problem is somewhat challenging. Like we know that RPKI data tends to propagate in 10 to 60 minutes, sort of, on the global internet. Is that good? Well, I mean, it's better than IR data that propagates in the span of multiple business days, but can it be done better? And what are the consequences of the protocol data encoding not being as efficient as it could be? If you have a fast machine and it's connected to the internet in Amsterdam, you might not have any problems. But if you are on a satellite terminal in the middle of nowhere and really depending on getting RPKI going with the limited resources that you have, then efficiency might be key. And so it's very easy to quantify Eric synchronization is less bandwidth than other synchronization mechanisms. But whether that matters or what the consequences are, that is hard to oversee at this point in time.
Sorry, I apologize. I forgot to use the the thing for the queue. Tim Ruijsels here. My name is on the draft with Job, so I have some interest, I suppose. And I support the idea. Otherwise, I wouldn't be there.
Oh, I'm so happy to hear that.
On discoverability, I think it's a bit early to really decide on it. I think definitely building up experience around if you want to put this into the RPI itself and looking at updating private key RCs, which is a new topic, presumably certificate profile issuance and everything around it. Or you could think of it into a method of PCAs and looking at whether it is. And you could also think about whether it might be better to have application servers communicate whether relays are or go with the
Put it in the DNS. Yeah.
I'm a DNS guy, not a PK guy, and I'm not saying put it into DNS, but what I wanted to say is that the problem we are trying to solve with the discoverability of the relays is essentially the same problem as we solved for DNS like 40 years ago with root servers for DNS, right? That's exactly the same problem. Half of the room is DNS people in here, so perhaps you can sit down over lunch and talk. What we did, what worked, what didn't. Perhaps there is lessons to be learned. We'll see.
Yeah, just.
Don't break it.
Maybe you have to put it on the floor.
I don't have anything that interesting to say, so. I'm assuming one like not supposed to fuss with their stuff. But...
So while you play with batteries in a banana-shaped thing.
I can ask the question, you can repeat. Oh, hello. Oh, good. No, it works. Yeah, Joe Abley, Cloudflare. So I was going to say that if the only real reaction from this is how do we discover the service, that's kind of a good reaction to should we deploy this. And my question really was: you've talked about this before? Have you heard any other concerns about doing this, or is this happening at this point?
I think it's happening. Yeah, it's almost suspicious, right? Why is there no? Where's the downside?
I mean, the only other comment I had is with NTP, we ended up with something like Ask runs a nice service, pool.ntp.org. It's nice, but it was bolted on after the fact, after we had a lot of headaches from things being hard coded. Maybe there's an opportunity here, as Rudy was intimating, to get ahead of that this time and not have to try and bolt something like that on afterwards. I mean, if the overhead is we have some trusted organization that runs pool.eric servers something, then maybe that's a reasonable thing to imagine.
Yep. Yeah, and other fun considerations are: do you want to run this over HTTP or HTTPS, or should we have relays on both? You can run a relay on a literal IP address. So I think using 1111 is a feasible path to exclude DNS from the chain of dependencies, but not, of course, the only path. And given that the RPKI interacts with the very routing fabric itself, circular dependencies are a concern in the RPKI. And I think the ability to run the ERIC protocol over, with or without DNS, with or without shared trust anchors on a TLS level, is very appealing, because it means we can increase the chances of relying parties being able to reach something of the RPKI substrate, and from there on, hopefully, it helps establish network connectivity on a wider scope. One of, I think, Mr. Volk.
Just on another aspect, in the very, very early days, I was running relying parties, and I learned that way that actually operating a relying party requires some attention, because, well, okay, data can get stale, and at least back in those days, the repository operators not always were fine. Well, okay, that was still experimental time. The nice thing about this scheme quite clearly is that the end users on the edge of a system obviously get a much reduced load of responsibility to monitor their stuff, but kind of the responsibility of the ERIC relay operators becomes actually very essential infrastructure. And that's actually more important than the stability of the operator itself. And kind of the question whether you as an end user trust a certain relay operator or another one is something that also requires that you should be able to actually configure whom you trust. Yeah, of course, the trust in the content is secured by all the cryptographic mechanisms, but the operational stability is not.
Yeah. So thinking about the software packages I maintain, I'd hard code that a set of relays is used if nothing else is configured, but allow the operator to specify specific relays they'd like to use or no relays. That there's going to be a few configuration buttons to press for those inclined to do so.
So Tobias Fiebig again. I just wanted to follow up, clarify on Peter's point on like learning from the DNS for service discovery. So DNS was a protocol with that hard-coded list of addresses to go to, which is distributed with the software packages. Okay, good. That was all I just wanted to check.
Yeah. Yeah, and for those of you that wonder why is this called Eric synchronization, my friend Eric Bias died last year, and he was a big fan of distributing RPKI data. So when this thing needed a name, I thought, I'm going to name it after my friend, and that's how we'll remember him in years to come. So thank you all for your time, and catch me in the hallways.
Don't forget, there'll be another IEPG in 3 months' time.
Exactly what I was going to say, you see? So please think about what you're going to present in a few months' time. Thank you. Especially thanks for presenters. Thanks for everyone.
Thank you, cheers. No worries. Thank you, Jen. She did all the work.
No, you were replacing the batteries. I hate physical air.
Thank you for having me. Thank you very much for the thank you.